So let's start the exercise session then, if you don't have any general question. So let me go. So this week the lectures are mainly based on the cylindrical cavity modes. I mean, how we can accelerate particles in a cylindrical cavity, and how we can uh, get yeah, and to understand the cylindrical to understand the uh, electromagnetic properties, properties of electromagnetic wave in cylindrical cavities. Uh, we can start with maybe first a uh, simple what we call the pillbox cavity. So suppose we have this kind of. So I'll just recap some of the concepts. I'm not going to go into the details because that's all are done in the lectures. Okay, and we know that in free space we cannot have electromagnetic waves. We cannot accelerate beams in free space, right? We need a cylindrical volume in which we can have a standing wave. What we call waveguide. Okay, and there are two types of modes for those waveguides, called transverse electric and transverse magnetic mode. We know that in transverse magnetic mode, so trans we have the magnetic field component of are zero, in transverse direction as zero, are no sorry so we have field components in transverse direction and longitudinal component is zero, so Bz is zero. And then in transverse electric mode we have Ez zero, right? And since so this is the x and this is the y coordinate, like this, and then we have the longitudinal coordinate z. And also we have some boundary conditions, because we know that for conductors, uh, in conductors, field cannot present inside a conductor, so we have some boundary conditions on the surface of this cylindrical cavity, or this pillbox cavity. So the boundary conditions, these are just so tangential component should be zero at the boundary, of electric field should be zero at the boundary, and a normal component of magnetic field should be zero at the boundary, at the surface, or you can say. So what does this mean? So this means that so what is the tangential component here? Pawan, can you tell me, in this cylinder? So I'm asking what so suppose, so this is a in cylindrical geometry you can see what will be the cylindrical coordinates of electric field for this cylinder at the boundary. So we have these components, right? You have ER, E theta and EZ, right? Now which of them will be zero at the boundary? Which are the tangential components? E theta is tangential. Yeah, you're right. E theta and Ez, correct. That's it, right? Then also, so then, and for b also we have same br, b theta, bz. So which of them will be 0? uh, br will be 0, right? And is b theta is normal? Bz is normal on these side uh, walls, right? And b theta will be non bz. Yeah, b theta is not 0, that's what I'm saying. Bz will be 0. So br and bz will be 0 at the boundary, right? Okay. So yeah. So these are these are from basic electrodynamics, electro dynamics that you have studied in your bachelor's. And so then particular for when we have transverse transverse magnetic mode in the cavity. uh, so so in transverse magnetic mode, bz is 0, okay, and we have ez, electric field in the z direction, and its form is given like this. So I'll just write out, this is Bessel function, dependence on r, then theta dependence on cos dependence on theta, and cos dependence on z, and exponential uh, dependence on time. Okay. So and so the main so the basic thing that we so I'm not going into detail into the derivations. So only thing that I will discuss is what kind of modes can we have here in the cavity. So for example, so there are there are some numbers here, m, n and p, okay. So there are some restrictions on what we can have when we have this kind of cylindrical cavity. So here m is do you know what mn and p are? I think you have not gone through the lectures, you said, right? Okay, so okay, briefly I'll just write what these are. So m is yeah, I think you are the only one, but it's okay. If someone will join, we'll continue. Okay. So m is simply the number of, it's called number of full period variations in theta. Okay. So what does it mean with full period variations? So suppose this is your electric or magnetic field on the x-axis, and on the y-axis, and on the x-axis you have theta, okay. And so full period is of what, 2 pi, right? In theta we have cos dependence, so so one period is 2 pi. So if we have a component which has uh, this kind of electric field or magnetic field, so then we can say that it has m equal to 1, okay. So one full period variation is there in the theta. Or you can have in 2 pi, you can have like this. Okay, sorry, yeah. So this is m equal to 2, or you can have 0 also, no variation at all at 2 pi. So m equal to 0. So this is what here m means. Okay, and then similarly for n, what is n? So n is the number of times the field component goes to 0 in the radial direction. Okay, so number of zeros, you can say, of the axial field component in radial direction. So for example, electric or magnetic field. So suppose the radius of the cavity is r. Okay, then similarly you can have either just 1 0 like this. Okay, or you can have, so these are Bessel functions that I'm drawing. Okay, in the radial direction we have Bessel function, right? I showed you. So this is j0, and sorry, this is for n equal to 1, this is for n equal to 2, and yeah, and this goes from 1 to 3, not 0. Okay, and we exclude the 0 that we have on the r equal to 0. So excluding r equal to 0. Okay, and then lastly we have the p, which is the number of half period variation in z. Okay, so for m we have the full period variation in theta, but in for p we have half period variation. So for example, suppose you have a magnetic or electric field as a function of z. Okay, then, and your length of the cavity is L in the z direction. So if you have the electric field like this, okay, this you can say it has a p equal to 1, because it is half the period, right? And if you have like this, so it is one full period, so two half periods, so p equal to 2. Okay, you get the idea, right? Yeah. So yeah, this is the concept behind m and p. And similarly you have transverse electric mode. uh, in transverse electric mode you have you have bz has a form given as this. So again, Bessel function, dependence, r dependence of, and then cos dependence of theta, and sine dependence on p. Okay, and time dependence like we had in the transverse magnetic mode. Okay, so yeah, these things we have. And so have you studied these things earlier, like what are waveguides, uh, why we need waveguides? Oh yeah, yeah. I mean, in the week 4 we had this, right? So yeah, here we have uh, cylindrical waveguide, and so that's why we have three parameters there. Okay, m and p. And okay, so So yeah, these are basic then also there are some other concepts like do you know what skin depth is? So since we are working with a conductor here, it cannot be perfect conductor, right? So fields can penetrate inside the conductors, and there can be power dissipation. So that's where the skin depth comes, and so skin depth is basically is the measure of how much uh, how much the electromagnetic waves are penetrating inside the conductor. Okay, and it is given by this simple formula. So here the sigma is the conductivity of the uh, metal, and mu is the permittivity, and omega is the frequency of the electromagnetic waves, right? Okay. uh, yeah, and then yeah, okay, so let's go with some exercises, okay, and based on these simple concepts, and maybe you need to go through the lectures and to understand everything again, okay, in detail, but I'll just go through some of exercises, okay. It will These are very easy exercises. So just I discussed. So can you tell me which of the following modes cannot exist in a cylindrical cavity? So there are some modes here. So like I said, there can be, so M and P, three parameters are there. So there are four options. Do you have any idea which will not exist in a cylindrical cavity and which will do? So yeah, but how can we determine? Okay, so let's go again here. So as I mentioned, uh, so we have these boundary conditions, right? And we have this form of electric and magnetic field. Uh, so based on these, we can see. So okay, let me write the it. Yeah, yeah, exactly. So for example, we have EJ. So yeah, for transverse magnetic mode, we have EJ equal to cos P by Z. Okay, this is we have, and then for BZ we have, sorry, yeah, that is a, huh? Yeah, this is for TM, transverse magnetic, and this is for TZ. You can read it, right, clearly. Okay, so now you see. So for first we see with the 210, okay. So what do you think? uh, to, will the 210 is the 210 allowed? So this is for transverse electric. So if you put P0, what will happen? Yeah, it exists, right? Nothing. nothing, there is no problem, right? Okay, so and then for the B option, 0 1 1, what do you think? How? Mm-hmm. So yeah, but okay. Uh, so in the transverse electric mode, okay, so the first option that you said exists, it will not exist actually. Do you know why? Because cos 0, if you put p is equal to 0, oh sorry, this is sine, that's what I'm saying. Sorry, it's not your fault. Yeah, now you say. Now if you put z equal to 0, pz will be 0, right? So then what is the problem? Why can't we have bz equal to 0? We have other components, right? We have so in the transverse electric mode we have e- no, e will why z will be 0? Ez is 0, but we have er and e theta are there, right? That is not the problem. The problem is so as I mentioned, now since bz equal to 0 at boundary 2, right? From the boundary condition, we know this, right? Because bz is the normal component, it should be always 0 at boundary, correct? And since bz is 0, uh, 0 inside of the cylindrical cavity, then it is 0 everywhere, right? And the er and e theta, they depend on bz, so they will also be 0 everywhere. Yeah, that's not problem. These notes will be available on the website. Okay, you don't have to note anything. These notes will be available, and these are explained in the lectures too in detail. So that's not an issue. Just I'm just explaining something so that you know you get the idea. So okay, then we have other options. So yeah, 0 1 1, it will exist, right? There is no problem with 0 1 1. And what about 101? Let's see, since you don't have any notebook. So in 101, so m is 0, right? So if m is 0, hello, Pavan? Yeah. Oh, I thought you cannot hear. Yeah, since m is equal to 0, what will happen is, uh, and it is a transverse magnetic mode. So, and what will happen? Yeah, but uh, but we have a problem here. See, what I told you. Oh, sorry, the 0 is for n, not n. Sorry, sorry. But I told you that in when I was explaining here what n is, it is the number of zeros in the axial field component in the radial direction. Okay, so this this is the axial component. Yeah. So this, suppose this is the axial component. It should go zero at the bond at the interface, right? If we have n equal to 0, then it will not go 0 at the boundary, and then we again violate the boundary condition, correct? So that's why we cannot have n equal to 0. N always starts from 1. Okay, you understand what I'm saying? So what is n? You can't understand what is n? Oh, like I said, it is the number of zeros of axial field component. How many time it goes 0? Okay, excluding at the r equal to 0 here. So here you see 1, 2. Okay, that's why n equal to 2. Here only ones, so n equal to 1. You see? So we cannot have n equal to 0, because the field should go 0 at least at the interface, right? The axial field. Because otherwise we'll have we violate the boundary conditions. We don't we cannot do that. So that's why n cannot be 0. So yeah, this one is also not allowed. The option C. Option C is not allowed. Option A not allowed. And then option D is allowed. 2 and 0 is in transverse mode. Even if the P is 0, we have EZ here, right? Yeah. So okay. So you have to think like this. Looking at the boundary condition, you can make sure which modes are allowed or not. Okay. So here is a vector diagram of fields inside the cylindrical cavity. Okay. So this is the diagram for magnetic field, and this is for electric field. So I'll draw the axis here actually. So this is the radius. So you are looking at the at the side disk of the cylinder. So this is the radius r, and here this is the length of the cylinder. Okay, so this is the z direction, and then so suppose, and this is the radial direction here. Okay, so we have to find the uh, we have to identify the modes. So what mode it is in, if it is in transverse magnetic mode, and if it is in transverse, which transverse magnetic mode it is in. Okay, so that we have to find. So simply from this diagram, you can say that it is in transverse magnetic mode. Which mode M and P will figure out later, but you can just simply say if it is in transverse magnetic or transverse electric mode. How, Mm-hmm. So how, looking at the diagram, you can say that it is in transverse electric or transverse magnetic mode. You have, the condition to have the transverse electric and transverse magnetic mode, right? This is the condition. Uh, so this is the condition. In transverse magnetic mode, uh, Bz is 0, and transverse electric mode Ez is 0. Okay. So what do you think it is here? So as I said, this is the z direction. Uh, this is the z direction. This is the r, and this is theta, right? And this is the diagram for electric field. So you see here Ez has some component, right? Ez is not equal to 0, so it cannot be transverse electric mode, correct? So what it is then, it is transverse magnetic mode, right? Because these arrows, you see these kind of arrows you can see, right? So it means that there is an electric field component Ez which is not equal to 0, correct? There are field vectors in the direction of z. Okay, so now we know that it is in transverse magnetic mode. uh, how do we find out the value of m, n and p? Okay, so yeah, number of variations. So simply, so for example, as I said, first let's look at the magnetic field, okay, in the theta direction. Okay, here this is the magnetic field, right? So you see, in theta direction, what we have, suppose if you make a circle like this, uh, a circle like this, okay, at this point, uh, suppose at this point, point 1, you see only radial, the magnetic field is facing on the only the radial direction. So here it is 0, right? B theta. Okay, so you start from 0 and then you go to a maximum value here, okay, and then you come again to 0, right? Like this, okay, and then you go again to a maximum value and come again to 0 when you go to 2 pi, right? So that means, what is the m value here? 1, right? 1 full variation, correct? That's what the m means, right? One number of full period variation in theta. So we have just one, correct? And then also, for you can see for the electric field, here you can see the Ez. So you see for Ez, you start with, in this direction you go, right? This is the z direction. You start with a electric field component in then Ez, and in the middle you have uh, yeah, or you can uh, this is the, oh yeah, sorry, yeah. So in Ez you have a maximum value at the starting. So suppose this is 0, this is L, you have a maximum value at uh, 0, right? And then it goes to 0 in the middle here, correct? You don't have any z component anywhere in this line, right? And then again you go to a maximum value in different direction. Here direction changes, right? And so you have how many variation you have here? You have 1/2 uh, period variation. So p equal to 1, right? And then again, in the radial direction you can check what is the variation of Ez is. So in the radial direction, in this direction, so you start from the axis, so this is the middle axis, z axis, and go in the radial direction. What you find is, uh, starting from 0, okay, you have so we are checking the variation of z component of electric field, okay? in the radial direction. And so you see at this point you don't have any radial variation, all the field lines are aligned in the z direction. So it is so here all the field lines, so it is the maximum, and then again it goes to 0 at the interface, because as I mentioned we need 0 at the interface, right? So here n is 1, we have only 1 0, and this is the Bessel function, this is j1 that we are seeing. Okay, so then what we find, we find that m and p is 1 1 1, so this is tm 1 1 1, right? So this way you can figure out what kind of mode is this from the field lines. So an exercise for you now. Can you see this picture? Okay, so yeah. So first let's find out if it is a TE mode or a TM mode. Again, you know the condition, right? In TM mode, what we have? We BZ0, and in T mode we have EZ0, right? So now you so this is for TM and this is for T. So now you tell me which one is there in this picture. Can you find EZ0 here? So you, again, this is the magnetic. Now here the figures are switched. This is now the magnetic field lines. Okay, this is the z direction. This is the r, and this is here your theta. Okay, and this is electric field in the right side. So what do you find? This is TM or TE? What? No, no. This is the electric field and magnetic field of the same cavity. Okay, in the same cavity, just the different point of view is shown here. Because now you see, so let me explain again. Yeah, it is TM. Why? Do you find BZ0? BZ is here, right? In the here you see, in the this is magnetic field first plot, and it has magnetic field in the z direction. So BZ is not 0. So it cannot be TM mode, right? Correct. So this should be in T mode, transverse electric mode, right? Yeah. So now we again have to find the M, N, and P. Okay. So so again, for the electric field, now here, uh, since it is in a transverse electric mode, Ez is 0, right? So then we'll have only the radial component, axial components. Okay. So ER, we can check ER here. So this is the electric field, the second plot. Now you see how it is changing with theta. How many cycles are there if you go round? So let's again draw a circle like this. Okay, so here you have maximum ER, right? Then is go to 0, then again. So so yeah, or start from say 0. So it goes maximum, then goes 0, again maximum. So four times it goes maximum, right? Like this in 2 pi. So that's why here m is what, 2, right? Yeah. And uh, then we can look at bz, because bz is not 0, okay, as a function of z or r, but will so as a function of, when we look at a function of z, it will give us the p, okay. Mhm. Here, oh, the magnetic field. So so this is the uh, this is the transverse view of cylinder, and this is the longitudinal view, okay. This is the direction of z, and this is the radial direction, and magnetic field vectors are plotted, okay. Now in the z, if you go in the z direction, what you see, what is the bz, what happens to the bz, huh? Yeah, it exists, I know, but how does it change? So for example, uh, so so you see in the edges, you have you don't have any jet component, right? These are curled, like this. The components, magnetic field components, are like this, and here they are like this, okay. And in the middle you have in them in the jet direction, so it is varying like this, right? In the length, and so this means that p equal to 1, half length, half period variation is there, correct. And then we can check the radial variation of also of bz. So you start from here, okay. Here you can see the field is 0, right, at r equal to 0. And as you go into radial direction, uh, you see a maxima, right? And since it is the jet component of magnetic field, it should not be 0 at the interface, it need not to be 0, right? So that means this is n equal to 1. Right. No, okay, I don't know, some problem. So it is n equal to 0, okay, n equal to 1, sorry. So what we have finally is m equal to 2, n equal to 1, and p equal to 1, okay. So it is transverse electric to 1 1 volt, okay. So you get the idea, right? So yeah, in the lectures too also there are many okay. So what is the yeah, in the lectures they are also explained very clearly, you can also go through them, okay. Okay, then next problem. So yeah, since you have not gone through the lectures, I'll little bit explain what this Kilpatrick limit is. So uh, so so what can happen inside a cavity, since you have electromagnetic waves inside the cavity. uh, there can be breakdown, right? I mean, at high frequency, there can be breakdown. So the Kilpatrick limit is a limit on the frequency, uh, which after which there is a possibility of breakdown. So yeah, no, since I already answered it, so it depends on the RF frequency that you are providing to the cavity. Okay. So yeah, again in the lectures there is detailed discussion. Okay. Okay. So a simple question here. So we have suppose a TM010 mode. Okay. Uh, Now the question is, the frequency of TM010 mode in a pillbox cavity depends upon which of these parameters? Does it depend on length, radius, neither length or radius, or both? Can you guess? No idea? Okay, so yeah, I mean, for this you need to know the formula for so I cannot able to write. So I'm not able to write properly. Okay, so the frequency is having some problem with the pencil. Let me try. Okay, so the frequency of TM mode, uh, it is I don't know. Some problem is there. Different color work. It's not about the color, I guess. Sorry, give me some time. Uh, yeah, now it's working. Okay, so yeah, so as I was saying, so the frequency of the TM mode is given like this. C is the speed of light, speed of electromagnetic wave, and there is a quantity called xmn, which depends on the k, the, and then this is the radius of the cavity, and you have the p dependence like this. So yeah, as you can see, the frequency is inversely proportional to the radius of the cavity. Okay, and since it is 010 mode, uh, this quantity goes to 0, right? But you still have this one, so it only depends on the radius, not on the length. Okay, so yeah, it's just you need to know the formula to get the answer. uh, in the exams, No, no, no. In the exams, there will be, I think, MCQ questions only. Not you don't need to derive these formulas, because these are not from this course. We are using these concepts from electrodynamics, correct? Yeah. So you just need to know the form of the all the equations. You don't need to derive anything, I think, in the exams. Okay, then again, a simple question. So suppose we have TM012 mode, okay, in a pillbox cavity, cylindrical cavity. Now, can you tell me the fields which are present? So I'll write out the. So we know that in TM there is no uh, Z, uh, BZ is 0, right? So then which of the fields are present? EZ, we know EZ is present. EZ is given by this, right? But other than EZ, what field will be present? Can you guess? Hmm? Which one? Yeah, EZ is present, we know. Then what about B theta and and ER? So we know that BZ is not there, so D is not the option, right? EZ we know. Then what about B theta and ER? So again, like for this uh, you need to go through the lectures, because uh, uh, because we know that the B theta and ER, they depend on EZ, but there is one catch. Since here m equal to 0, right? So what will happen is ER will not be present, okay? ER will be sorry, ER will be 0, okay? Because ER has there is some noise coming, Pavan. It's okay. Yeah. So ER will be 0 in this mode, okay? Uh, yeah. So yeah. So this is from this is, you can also see from the boundary condition, right? ER is the tangential component, right? Oh, no, no, no. ER is not the tangential. Sorry. ER is the normal component. Yeah, it doesn't need to be 0. Uh, D theta is also not 0. But I need to look at the. So, so mm, I think ER has sine m theta dependence. Uh, am I right, sir? Hello, sir. Are you there? I think he's not here. But yeah, I think it has sine m theta dependence. Okay. And since m is 0, so that's why ER is 0. I don't remember the exact formula, but yeah, because Ez has cost dependence, Er should have sign dependence. Okay, but anyway, I'll check. Yeah, I think this is the region. Hello. Okay, I'll check. Maybe also you can check. Okay, what is the radial dependence in transverse magnetic mode? Okay, then we have a question. So there are some fields of merit. Okay, uh, for a cavity. I mean, for a resonant cavity. So I'll little bit explain what are these fields of merit. To determine which is a good resonant cavity. Okay, so there is a term called quality factor. So as the name suggests, uh, it is a ratio of stored energy, okay, per unit power dissipation. So you are supplying some power to the cavity, right? How much it is storing and using it to accelerate your beams. So that is the uh, that ratio is called quality factor. Okay, it is given like, so it depends on the frequency, then energy, and the power dissipated. Okay, the ratio. You understood? Okay, so energy stored per unit power dissipated. And then the second one, the resistance. So shunt resistance is given as V square by power dissipated. So what is V square here? So V square is the axial voltage produced, okay, inside the cavity. And so the meaning of this is, so axial voltage accelerates the beam, right? You know that. And so what this shunt resistance means is the acceleration one gets for a given for per unit power dissipation. Okay, how much acceleration you are gaining. Okay, and then you have ratio of this, so rs by q, which is the third option. It is given as r by q, so it is same as r. Okay, and then the frequency the resonant frequency, rf frequency. So these are the options you have, and the question is which of these does not depend on the properties of material. So do you know, can you tell me which one? I explained to you what these terms are. Can you guess? So, so first, quality factor. It is the ratio of energy stored per unit power dissipated. So, what do you think material has to do in this, to storing the energy in the power dissipation? Yeah, yeah. So then it depends on the material property, right? Quality factor. Okay. Yeah, see, because when we take the ratio, it cancels out, right? Yeah. So yeah, correct. Good. Okay. Yeah, you will also learn this detail in the lectures. Again, we have same kind of question. So skin depth, skin depth, right? I explained you skin depth. It doesn't depend on which of these. So conductivity, permittivity, RF frequency, radius of the cavity. So which one is the correct option? Can you guess? So skin depth, yeah, conductivity, obviously, because the waves are going inside the conductor. So how much how deep it penetrates, it should depend on the conductivity, right? Yeah, radius, because radius has nothing to do with the skin depth, right? Simple. And also from the formula, so I wrote down the formula, right? It was this. So all the three parameters are here. Radius is not here. Okay. Okay, then a simple numerical problem we have. So we have 010 mode, TM1010 mode, and the frequency that it's operating on is given, suppose 4400 millihertz, and this factor x01 is 2.405. It is also given. So you need to calculate the diameter of the cavity. So so how can we do that? So I wrote down the formula for frequency, right? Yeah, P will be 0. So we have just 01 square divided by r square. Radius we have. So you can put everything. So 4000 millihertz. Let's keep it in hertz. C we can meter per second. 2 pi is 6.28 almost. X01, so it is both squared and under root, so we just take it out. 2.405 divided by, so r is what, d by 2, right? So we multiply here by 2, and we can easily calculate d. So it is 3 by 4, and the 10 to the power 8 cancel with the so here we take 20 from here, it becomes 10 to the power 8. We cancel it with that, and 2.405 into 2 by 6.28, right? So this goes 2, and it is so multiplying the above 3 with 2.40, it gives you how much? 7.2, right? On 5, right? And then you have in the denominator 12.48, correct? Hello? Oh, sorry, 12.56. And so roughly you will get a value, if you divide this you will get a value in meter, right? Roughly, like, I mean, seeing these options, I think you will get something like 0.57 meter, correct? Because it is almost double. So yeah, 57.4 centimeter is the answer. Okay. Then one more numerical problem. Uh, Skin depth of in copper. So I just wrote down the formula for skin depth, right? What it is? Sigma mu omega. And here 1 by sigma is given. So just 1.7 into 10 to the power minus 8. What is the value of mu? Oh, sorry, yeah, that will cancel with the otherwise. Okay, so 1 by sigma is 1.7 mu is what? 4 pi into 10 to the power minus 7, right? And then we have uh, 2 pi f into, so it is in megahertz, so it will go here 10 power minus 6, correct? Okay, so let's calculate a bit. Let's see if we can convert to an answer. 2 equals 2. So here in the above we have 10 to the power minus 14, here 7. So what remains is 10 to the power minus 7 in the numerator, and 1.7 in the denominator. We have 4 pi square into 500, correct? And what should be the what is the value of pi square roughly? 3.14 into 3.14, it is 9.85. okay, so and let's multiply that with 5, so we have 49.29 into 4, and let's take these two zeros above, so we have 10 to the power minus 9 into 1.7, okay, and multiply 4, so we have in the denominator 1.7 by 197.192, okay, and what we can do is, and here 10 to the power minus 9 is there. I'm taking it this side. Okay, I'm doing on the calculator, so 1.7 divided by, sorry, yeah, it comes around 0.0086, okay, so yeah, and we have 10 to the power minus 9, right? So roughly you will have, so if you take square root, I think it will come around if you take the square root of point 0.00086, I think I did some mistake. I'm getting a value like 3. I'm getting a value 9. And the answer should be the order 3 or something. But yeah, I mean, okay, I think we did some mistake. Yeah. Should be so I'll tell you the answer. The answer is, I think, 3 micrometer. Okay. Okay, you can check this again, or maybe sums are wrong. I don't know. Okay, I'll check it. I did not do it before. So yeah, it's trivial. So this was the last problem. So yeah, since you have not gone through the lectures, it took little long, but these were really simple problems. So I'll suggest you once go through the lectures, and if you have any doubt, you can ask again in the next session. Okay. And I'm not sure why others didn't join today. Maybe did you got any mail for today's session or something? Also mails are going, but I don't know. Maybe some issue. Okay, so let me once ask if sir is. So hello sir, can you hear us? Okay, okay. Sir. We lost you little in the. Okay, okay. Uh, so so yeah, I finished. I'm finished with my exercises. So yeah, Pawan, go on.